welcome back. If you are here, that means you probably watched the Sigtunnel demo. If you didn't, that's totally fine. I will leave the links in the description below, that way you can catch up. In this video, I'll cover the overall system architecture behind Sigtunnel. And hopefully after watching this, you'll have a better understanding on how the platform was designed and how does it work in general. So let's get started. All right, so over here, we have a complete system design diagram of the platform. And it's important to point out that everything you see here was provisioned using infrastructure as code, more specifically Terragrunt and Terraform. We're not going to cover the code right now, but I even produced a quick manual here that you can follow step by step. And we have this one-click deploy where we get all of those components out. So everything very automated. Now, let's talk about the design itself. Everything starts with a user, right? And if we recall our demo, the first thing that happens is our user loads a web application, more specifically this one. And the first thing the user is doing is typing this URL on their browser, and this URL needs to be resolved into something, right? So the first step is we have domain name resolution, and that happens in our AWS Route 53 hosted zone. So our hosted zone is then able to resolve this domain into something. And the something we're looking for here is our web app statics files. So I think it's important to mention right now, this application is a single page application. So we're basically looking at static HTML, JavaScript, CSS, image files, and SVGs and whatsoever, pretty much static files. And for that, we can leverage a CDN service, like a content delivery network. And more specifically, we're leveraging CloudFront, which is AWS offering for a CDN. And what CloudFront is doing for us, the CloudFront distribution to be more specific, Amazon has a bunch of computers, they call them edge locations all across the planet. And those edge locations are machines specialized in serving requests. In this case here, the request for serving is, pulling those static files. And those static files are then hosted in an S3 bucket, a simple storage service bucket, which is also another Amazon service that is specialized in working with storing like files, pretty much unstructured data. So again, whenever the domain is resolved, our user is then making a call to this CDN service to an edge location, and the edge location, if it's a cache miss, it's then going to go to our S3 bucket, fetch the files, and then load the files. Then if we have a second user trying to load the application, the files are already going to be on the edge location machine cached over there, right? Also important to mention that the CloudFront distribution is connected to ACM, which is a certificate manager service from Amazon, which means that this whole communication here is done in HTTPS. It's encrypted. So it's a secure connection, fully encrypted here end to end. Now, once the page is loaded, and we can see the page over here, next up, we need to log in, right? So the user is going to either provide their email and password, or they're going to sign in with Google. And whenever doing that, what the user is actually doing is making a call, an API call, Amazon Cognito user pool. What the service, it's yet another Amazon service, and this one specifically implements for us the authentication and authorization functionality that is required for our platform to function. So yes, I could develop my own microservice to deal with user management, like storing password, encrypting passwords, but this offering from Amazon, it's pretty cheap. It's very scalable, so that way I don't have to scale that microservice specifically. And it also comes with a lot of plug-and-play integrations with third parties, like single sign-on with Google, Facebook, and other providers. So that's pretty handy, and that's why we're leveraging it over here. So again, that request is going to come from the user to the Amazon Cognito user pool, and once the identity of the user is verified, we generate a set of tokens, more specifically two JWT tokens, two JSON Web Tokens. One is going to be our access token, and the other one is our identity token. The access token pretty much defines our access, like what is the user authorized to access, and the identity token is mostly used on the front end to pre-populate some information about the user. Once the JWT token is generated, it's then stored on our web application, and it's used in subsequent calls to our API. So whenever we finish logging in, our web app will redirect ourselves to a dashboard page. And this dashboard page is composed of a bunch of information, and that information comes from our API, as you guys can see here. And we can also see that authorization is done through like our JWT token. So, well, obviously, in order to find the API destination, we need to do DNS resolution again, but skipping that step, the API request will then navigate to yet another CloudFront distribution. But this one is a little bit different. Besides ACM, like besides having a certificate, meaning that it's an HTTPS call, it's fully encrypted, we also have another interesting system component here, which is our WAF, our Web Application Firewall. And this component here is doing rate limiting and bot control in terms of the requests we're getting to our CDN. So for example, if someone makes let's say 60 calls in a single minute to our application, we may tag this user or this IP, to be more specific, as someone that we're not interested in serving requests. And we can start blocking those requests and returning a 400 code back to the user, right? So the web application firewall is just a way for us to block inadequate traffic right on the edge. Another interesting thing to mention here is both of our CloudFront distributions, they produce logs, and that's going to be important for later. And those logs are stored in also Amazon S3 bucket. So we have an S3 bucket for our API CloudFront distribution, and we also have an S3 bucket for our web app CloudFront distribution as well. Those logs are going to then going to be useful for us to introspect on the service on the system and also observe it, right? But anyways, going back here, our API calls are then going to this CloudFront distribution. And from that point on, it then dispatches that request to a application load balancer. So let's talk more about that. The load balancer is a component responsible for receiving requests and redirecting those requests to healthy nodes. What do I mean by a node? You can imagine a node is a server running a copy of your code. And at some point, you may have multiple servers running your code. The load balancer's responsibility is identifying which one of those servers are healthy to receive requests. And within that group of servers that are healthy and good to receive requests, the load balancer needs to use a distribution strategy to determine how it's going to distribute traffic between those servers. One of the most famous ones is round robin, where the load balancer pretty much sequentially distributes traffic across each one of the servers, making sure none of them are idle. Now, there are many strategies. We're not going to cover them here, but that's pretty much the nuts and bolts of what a load balancer does. Now, we have an application load balancer. This means this load balancer sits on layer 7 in the OSI network model, meaning that the load balancer understands application-level network protocols, such as HTTP or maybe FTP, for example. Now, why is that important? Well, that's important because all the requests we're receiving all the way from the user here, those are HTTP requests. They are navigating to our CDN, and from our CDN, those are being dispatched to the load balancer. The load balancer is then capable of doing SSL termination, meaning that it unencrypts the payload, and it's able to look at the HTTP request and understand its payload, its headers, and pretty much everything that involves an HTTP request. Its URL, for example. So, well, let's understand how this can be leveraged in our case specifically, right? In our case, we are doing a request to our API domain over here, but then we have a /platform-API here. So what we can do here, and what we're doing right now on the ALB, is defining a targeting rule, basically saying, hey, whenever you see /platform-API, you should send traffic to a group of machines. And obviously within that group of machines, the machines should be healthy. So that's very important to understand. Now, besides application load balancers, Amazon also offers network load balancers. Those are sitting on layer 4 on the OSI network model, meaning that they only deal with TCP and UDP protocols. The advantage of a network load balancer over an ALB, for example, is that it doesn't have to understand, again, application level protocols and introspect into those packages to decide where to route a request, right? So network load balancers, they tend to be lower latency. They're pretty much like just sending the package ahead, and they're especially useful when dealing with streaming applications, for example. Now, in our case, we actually take a lot of advantage of understanding what's happening in our HTTP package. So an application load balancer makes a lot of sense, and it doesn't incur too much latency in our use case. So that's why we're using it here. Besides that, there are some other advantages. Like because the application load balancer is dealing with HTTP packages, you can actually connect it directly to a service, let's say like WAF, to do rate limiting or even verify if the request has SQL injections or any other sort of dangerous payload. So those are some of the advantages when comparing those two offerings. Another important detail is that our ALB produces logs, and those are being also stored in an S3 bucket, very similar to what we're doing with our CloudFront distributions. That's important because eventually, when we talk about observability, this data will come in handy. Now, going back to our end-to-end example, the user makes an HTTP request to our CloudFront distribution, and then that CloudFront distribution sends a request to our ALB. But we're going to notice here that our ALB sits inside of a VPC, a virtual private cloud. So let's talk a little bit more about that. Now, you can think of our virtual private cloud as a router that we are renting in an Amazon data center. And you can think of a data center as an availability zone pretty much. Now, this router makes it possible for us to create a network, right? And within this network, we're going to have public and private subnets. So let's start with those, right? And you can imagine that a public subnet, it's a subnet that is it's part of the network that is capable of receiving traffic from the internet. So ingress and egress, in and out. And the private part is not accepting traffic from the internet, from the public internet. It's mostly dealing with its private components here. Now, why is that important? Well, that's important because we have, again, going back to our flow, our CloudFront distribution is sending traffic to our application load balancer that is sitting on a private subnet. So how is that possible? Well, that's possible because Amazon offers a service called VPC Origin, which pretty much whitelists our CloudFront distribution to have access to our private subnet. It's a fairly new service, but well, in the past, you would need to actually have your application load balancer in a public subnet, meaning that it would be accessible by on the public internet. So this is an interesting development from Amazon there. But well, let's go back to the end-to-end to understand how, the traffic, like the route of our package so far. Okay, let's do a quick recap. We know our user just opened the dashboard page of our platform. And by doing so, the web app is dispatching a bunch of HTTP calls to populate this data, right? And those calls are going to our API here. Now, we know the API calls are then being received by our CloudFront distribution. And then from that point on, the CloudFront distribution dispatch those to our ALB. That sits within our virtual private cloud in a private subnet. That all looks good, but you may be wondering, why not have this ALB in a public subnet and just send traffic from the user to the ALB? Well, there are a few reasons that, like sending traffic to a CloudFront distribution is actually beneficial. The first one is caching. Some of the routes, some of the API routes that we're going to serve, maybe there's data that will be static, meaning that the data doesn't change over time. Think of an endpoint that returns a list of countries, right? That endpoint will rarely change. So we can actually leverage CloudFront here and cache that information. So the first request would actually go to CloudFront, then go to the ALB, and then the service would then process the request, and then the request would come back, and then CloudFront could then cache that information. And whenever another user loads that page, or even the same user, then instead of going all the way to the ALB and the servers again, CloudFront is able to return the cached result. So caching is a big benefit of going to CloudFront. Another benefit is CloudFront works with edge locations. That edge locations is a fancy name for there are servers everywhere across the globe. In fact, in every single country, every single region, right? So the benefit of the user talking to a closer service, a closer server, is that latency tends to be shorter. And you may be wondering, oh, okay, but the application load balancer, where is it deployed? Well, the application load balancer is deployed in our virtual private cloud, which is sitting within a region, more specifically, an Amazon data center region. And Amazon has multiple regions. It has US East 1, US East 2, US West 1, but that region is bounded to a geographic location, right? So our ALB is sitting in our case here, specifically in US East 2, which means that it's in the US, right? But now imagine the user is in, let's say, South Africa. If the user is in South Africa and he needs to communicate with the ALB, he would need to do a bunch of network hoops across the internet to again reach to the US. And then from the US, and by reaching the US, it would be able to get to our ALB. And then from that point on, the request will be processed. And then the request needs to go in multiple hoops back all over the internet to get back to the user. Now, the benefit of using the CloudFront distribution here at first is that we're sending that request to this server that is nearby us. So again, imagining the example of the user in South Africa, it would send a request to this server in South Africa. And then Amazon has the benefit of having a private network that is capable of minimizing the number of network hoops to talk to this ALB that is sitting on, again, US East 2, for example. So there is a network benefit and a caching benefit of using a CloudFront distribution in this case. Great. Now that we know a little bit more about our networking strategy, let's talk about the servers. We know our application load balancer is receiving a bunch of HTTP requests, and it's passing those to healthy servers over here. But what are those healthy servers? Well, we can see here we're using Elastic Container Service, ECS, which is one of the many products from Amazon. But I would like to take a step back and talk a bit more about the many options we could have taken, because there's many ways to solve a problem, and there's a specific reason why I chose ECS. So the first option we have here, and I think it's the most basic one, is to rent a VPS, a virtual private server. And in this case, in the case of Amazon, we could rent an EC2 instance. Well, by renting a machine, you are responsible for choosing the operating system that machine is going to run, and you're also responsible for patching and maintaining the machine. So you have a lot of freedom, but you also have a lot of responsibility, right? Also, within that machine, you need to define how your process is going to run, right? Maybe you're just going to run your code, or maybe you want to run your code as part of a container. So you may want to install Containerd or Docker or something like that. But that's all your responsibility, right? You need to do all that installation, all that configuration, and all of that maintenance. Again, it's very powerful, but there's plenty of responsibility. You could scale your application even using EC2 instances. One way would be using ASGs, like auto scaling groups, meaning that you can put your instance in an ASG, and basically Amazon can capture metrics from your VPS, from your virtual private server, and generally like CPU, memory, storage, and based on that information, you can configure your ASG to clone that machine as many times as you wish. So going back to our application load balancer example, we could start with a single tiny server, a single tiny EC2 instance, and then write a set of scripts to replicate it depending on, again, those metrics that I've just mentioned. So that would be option number one. The upside is a lot of freedom. Customization is at your fingertips. The downside here is a lot of responsibility, security patches, maintenance, and again, especially for a project where we have a few engineers, or in this case, I'm the only engineer, I wanted something more practical, right? I don't want to manage machines update and pretty much having to do a lot of like IT work to make sure my application is running in a safe environment. So that's option number one. Option number two would be exploring something like ElasticBeanstalk, which is a fully self-managed service from Amazon, where pretty much you just package your code, send it to Amazon, and then they are responsible for configuring the machine, setting up the operating system, the runtime to run your code, and it's all managed by them. They even offer like a continuous integration and continuous deployment pipeline. So it's super simple to get started, but there's a problem. If your application is just running one monolithic service, or maybe a couple of services, you could fit all of those in, again, ElasticBeanstalk, which will provide a machine for you. And that's okay. And you'll be able to have those services as processes within that machine communicating with each other. Or maybe, again, Docker containers communicating with each other, right? Possibly like running Docker Compose or something like that. But the problem is, as you scale, like as you create more microservices, as you need more power, like networking power and control, ElasticBeanstalk is not going to give you that, right? You're still bounded to that single machine universe and running a few processes there. Also, if you want to take advantage of the power of that machine, you don't have many tools there, right? So let's say, hypothetically, you rent a machine with 8 virtual CPUs and you're deploying your code over there. You would have to manually scale your code or write some wrapper to run a bunch of like child processes to take advantage of the power of those eight CPUs, for instance. So again, if you're doing a simple application, maybe not a microservice, maybe you're just doing more of a monolith, and you're okay with scaling your EC2 instances like that, that's totally fine. But ElasticBeanstalk kind of lacks the tooling to orchestrate containers and have that networking bit for microservices in general, right? So, and there's better options that we can explore. Okay, option number 3 would be considering something like AWS Lambda, a fully serverless offering from Amazon. But well, how does it compare to the previous ones I've just covered? Well, the previous ones require us establishing a server. That means we're going to pay for that server 24/7, even when there's idle time. Now, with Lambda, we're only paying for code execution. So for example, if someone opens our dashboard page and that creates multiple API invocations, we're going to have either like multiple Lambdas or maybe one Lambda taking care of that request. And I'm only paying for that duration of that Lambda, like how long that Lambda took to run my code and send a response back. And that's pretty cool, right? So it seems it's a clear winner. Like Lambdas, you're only paying for what you use. But there's a few gotchas. With Lambdas, one of the gotchas here is cold starts, which means that the first user that is, for example, accessing my dashboard, they're going to make a bunch of calls to our backend, and Amazon needs to run the Lambda for the first time. And by running Lambda the first time, I mean that Amazon needs to get our code either in a Docker container format or just all the text that represents our code, or maybe a binary, and push that information to a machine, establish that machine, and then prepare a runtime. So anyways, it's doing multiple steps to make sure that piece of code that we want to run will be ready to run. So there's a cold start. There's a period that Amazon is taking here to get that code into a machine to run it, right? And that is a bit problematic because for our user experience, maybe whenever I'm loading the dashboard and I'm the first user loading the dashboard in a day, for example, I may experience some slow requests. So instead of like running in milliseconds, it may take a second, for example, or maybe a couple of seconds to resolve a request. And again, depending on the type of application you're dealing with or the type of experience you want to offer your customers, that may be problematic, right? I think Lambdas are a fantastic compute resource, especially when dealing with asynchronous compute, right? So when you're processing a job or consuming information from a data stream. But whenever dealing with real-time requests, it's tricky because it really impacts, again, the latency and the quality of our user experience. So in my case here specifically, I wanted the experience to be super smooth. So having to deal with cold starts wouldn't be the most ideal of options. And also, Lambdas have more limitations than cold starts. You could work around cold starts and try to warm up a Lambda. So try to keep your code running at least in one instance in Amazon, which is a bit tricky, but you can do it. But besides that, even parallelism is a bit complicated. So for example, let's say I have a Lambda running my system code, and I want to run more than 1,000 instances of my Lambda, well, Lambdas don't automatically parallelize. Like, I mean, they do, but at some point, you have a quota in your AWS account. So you need to bump that quota to run more Lambdas in parallel. So anyways, it's not magical. And it comes with a cost, right? Again, for internal systems that we are okay with the user experience not being the fastest, or again, for jobs that we want to run asynchronously, Lambda kind of fits the bill quite perfectly. But in the case here where we want to have a very smooth user experience with no cold starts, probably running a 24/7 server makes sure the experience is more smooth. Another option we can explore is either container orchestration services, such as ECS, or container orchestration platforms, such as Kubernetes. So in a very high level, Kubernetes is this platform, open source platform developed by Google multiple years ago, and it's still maintained by the community today. And the idea here is you may have a set of servers, like either in a cloud provider or in a physical data center or in a mix of both. And you want to install the Kubernetes platform into those servers. And what you get from that is a control plane, pretty much think of a set of workers and processes that control all the networking between the machines. And you also enable the machines to run container workloads, pretty much. So that's what Kubernetes is in a very high level. Now, Kubernetes is very powerful because first, it's open source, so you're not tied to any cloud provider. You could possibly run within AWS, but you can also run Kubernetes in your own data center, or again, a mix of both. And also the community is pretty strong, meaning that besides being a very powerful platform on like connecting microservices and again, containerized workloads, there's also a set of add-ons we can install to give powers for ourselves to observe what's happening with the cluster in terms of networking, the logs that are being produced by the containers. There's a lot of like open source projects surrounding Kubernetes that empowers it and makes it even a more interesting option, right? Now, obviously, by being this open source project, it also comes with a lot of responsibility. If we want to create our own Kubernetes cluster, that means that either we can go to one of those cloud providers, such as AWS, and use their services. Like AWS offers a service called Elastic Kubernetes Service, which gives us the control plane of Kubernetes, but we still need to manage our cluster in our machines. And it's totally fine, but again, it comes with a lot of like DevOps work, right? Setting up a proper Kubernetes cluster takes time and takes a lot of configuration and expertise. Given the scope of this project, again, Kubernetes could be an option, but I believe it would be a bit overkill. Also, it tends to be very expensive, especially if we're going to use EKS. If you're just using EKS and getting the control plane from Amazon, that's out of the door today, $70 that you're going to spend. And with $70, we can actually host pretty much the entirety of this design if we're not using Kubernetes, right? So it is a bit more expensive. It gives you a lot of freedom. It can run in multiple clouds, but at the same time, it requires a lot of man work and expertise to do it properly. So that's one option when talking about container orchestration platforms. Now, we also have container orchestration services such as ECS. So ECS, you can think of it as a closed source version of Kubernetes that was developed by Amazon. So in a nutshell, they are the ones, Amazon in this case is the one getting the machines running, installing all their closed source software, and making sure you can run your container workloads. And that's also, again, pretty powerful. In this case here, I'm the only developer in this project. I want to run my containers, but I also want to make sure I can scale this for the future. So ECS actually has the power to lead with that scaling. So what do I mean by that, the scaling? Obviously, we want to scale containers. So again, in this case here, we have our platform API container, and I may receive multiple requests to it, and I want to scale it and make sure my service is up and running and it has a good SLA-SLO. But besides that, we're talking about how the system evolves over time, right? I may want to develop other microservices in the future that will be sitting alongside with the platform API. And those microservices may be dealing with other sort of workloads, right? Maybe asynchronous, maybe synchronous, who knows? So I wanted to have this flexibility, and ECS actually brings that to the table. It has a set of like tools from Amazon that enables this networking between microservices, and it also empowers us running our containerized application in a scalable manner. So that's a win-win. That's a win-win, right? Another detail here is I've mentioned that EKS out of the door, just the control plane, can cost around $70 today, at least till the recording of this video, as of the recording of this video. Now ECS, you can start totally free with it. You can just have an empty container, an empty cluster for free. Another thing that is kind of interesting here for both ECS and EKS is that both of them can work. You can either like create your cluster manually. So you could spin up your EC2 instances or your virtual private servers manually, or in the case of Amazon, we have this service called Fargate. And Fargate actually, it's a sort of like a serverless, almost close to like ElasticBeanstalk approach, where we don't need to take care of the compute here. We don't need to actually boot up the server and maintain it. We just tell Amazon exactly what we need to run our container. So I specify how many virtual CPUs and how much memory I need for that container, maybe storage as well. And then Amazon is responsible for provisioning a machine or getting some space within one of its many machines and running my workload, my containerized workload. In this case, my platform API service. So right now we can see that given those four options I covered, I thought the Elastic Container Service was the most attractive of all of them. Given, again, it deploys containers, and again, my service right now is containerized. I actually run it locally using Docker Compose. We can scale the containers quite easily as well. So scaling out and scaling in, it's super simple. It's part of the ECS platform. Our services are going to be running 24/7. I'm going to be paying for the compute that a container takes, which is pretty nice. And I'll make sure I don't face any cold starts because, again, my service is running 24/7 and serving my API 24/7. The networking is, again, possible. So if I want to do microservices in the future, even encrypted communication between microservices, if I want to play with a service mesh, if I have a very complex use case, I have all the tooling to explore that with VCS. And again, we don't need to maintain servers, right? Right now, I can just tell Amazon, hey, this is how much memory and CPU and ephemeral storage that I need, and they will provision that for me. And I just pretty much supply my container image. And for container images, we're leveraging Elastic Container Registry, which is pretty much, again, a container image registry that is offered by Amazon. We could publish our images in, let's say, Docker Hub, which is a public container registry. I think it also has a private offering nowadays, but we're just going to creating a quick private repository in our AWS account where we can push our Docker image. So that's pretty much that gives us an overview of a few of those compute options and why we're pretty much going for Elastic Container Service as a solution. Now that we understand why we chose Elastic Container Service, let's talk a little bit more about it, right? So we have an ECS cluster here, and the first component we have inside our cluster is an ECS service. If you're coming from the Kubernetes universe, an ECS service is very similar to a Kubernetes deployment. It's pretty much, you can pretty much think of this as yourself as a developer, you declare a spec, a declarative spec. And in the spec, you have a set of rules you're establishing. For example, hey, I want a minimum number of copies of X copies of my service to be running, and I want a max number of copies of my service to be running at any given time, right? So for example, for my platform API, I can tell ECS, hey, I want the service to have at least 3 copies of it running, and you need to maintain those 3 copies healthy, and we can scale all the way to 8 copies. And not only that, on this spec, I'm not only telling ECS the minimum and maximum number of copies of my service, but I'm also giving them instructions on how to scale, right? So for example, you can tell ECS, hey, if the CPU and memory, or maybe if the ephemeral storage inside my task is over X amount, then you should scale out. You should create more tasks. You should create more copies of my service. So that's the way you should see a service in ECS at least. And this is a very important component here because it will enable us to scale our service out and scale it in as well, right? We can also establish metrics like, hey, for example, if our tasks are running on 20 CPU, maybe I shouldn't run as many copies. So I can downsize my tasks all the way to the minimum amount that I specified on my spec, right? So that's pretty much what a service is. Again, coming from Kubernetes, a deployment is pretty similar to that. And finally, we have a task. And a task, again, correlating that with Kubernetes. In Kubernetes, we have the concepts of pods, and within pods, we can host multiple containers. A task is the same thing in the ECS universe. A task is a way for us to define multiple containers. And in this case here, our task runs a few containers. It runs our API code, so we have our platform API container. It runs a NewRelic agent container, and we're going to talk about it. And it also runs a log router, a fluent bit log router container. Now, obviously the main container here is the service, right? But what are those other containers? Well, those other containers are what we call sidecars. And those sidecars are containers that are running code as well. But the responsibility of those containers is to collect information about the task. And more specifically, make sure that the platform API container that is running our application code is healthy. So the NewRelic agent container collects metric information of the entire task. And we can also collect metrics information about our platform API container. And our log router here, which is also running in a sidecar, is capable of collecting the logs that are being outputted from our platform API container. Both the NewRelic and the log router, the fluent bit log router, they dispatch that information. So this one is collecting the metrics, right? So imagine this agent here is collecting that the task is using, I don't know, 1 vCPU, and it's using 200 megabytes of memory, and it's collecting that information constantly and eventually bulking it and sending it somewhere. And the log router is constantly getting the standard output of our platform API process, collecting that information and sending elsewhere as well, right? So that elsewhere is, in this case, NewRelic. So NewRelic is an external provider, and they have an endpoint, and those containers pretty much are dispatching that information to that endpoint. And in order to do so, we're going to see here that both containers actually have AWS secret managers associated with them. And those secret managers here, they inject the necessary secrets to make sure that we are dispatching that data to our private account in NewRelic, right? And that we are authorized to do so. So that gives a quick overview of those sidecars. We can also see our platform API has a few of interesting configurations at the application level code. So this is a Quarkus Java app, again, RESTful API that I've developed. And whenever it faces any unhandled runtime exceptions, it sends that information to Sentry. So again, that's an application level configuration. This is the application code running here in this container is the one dispatching those runtime exceptions. That's and also we're going to see there's another configuration here, which is NewRelic OLTP, which stands for Open Telemetry. So pretty much like whenever any exception happens and I want to have a complete trace of what happened, I also send that information to NewRelic. So there's plenty of places for where we're leveraging observability here to make sure that, again, the system is healthy. And if it's something that happens, I can go either to Sentry or NewRelic or both. I can see the logs of the process, and I can also see an aggregated view of the exceptions and exactly what led to those exceptions. So very good observability here. Well, next up, we're going to notice that we also can notice that our task is connected to two IAM roles here, right? So those IAM roles here, we have a task role and an execution role. The execution role comes with all the authorizations for our task, our ECS task, to fetch our private repository Docker image. And our task role, actually, it's more related to the permissions our actual platform API code, our application code, will assume during runtime. So for instance, like for example, whenever our platform API needs to communicate with our RDS database, because we automatically are assuming this task role, our platform API service automatically has access to communicate with our RDS proxy. And we're going to talk about this proxy in a second. Another interesting point to cover here is, well, maybe, again, our platform API, no, not maybe, it's definitely talking to external services, in this case here, Sentry and NewRelic. Question is, how is this traffic leaving this private subnet and going to the public internet, right? Because those services are outside of our cloud. Well, the way we did that is by leveraging something called a NAT Instance. So there's many solutions to that. So let's cover this topic, right? So over here in our public subnet, we have a NAT Instance. NAT pretty much stands for Network Address Translation. So, well, you may imagine that all those components here, those containers, tasks, they have their private IPs. They have IPs within our virtual private cloud. And again, within this specific submask here. Now, how do we get those IPs, those processes, to be capable of talking to external services? Again, going back to NewRelic and Sentry as examples, right? For example, so, well, one of the ways here, one of the ways to do that that are fairly cost effective is we have an elastic network interface in our private subnet where we're able to dispatch our egress, so the traffic getting out of our container here, our application, let's say our platform API, or maybe our NewRelic agent or log router, they're able to talk to this interface. This interface is connected to a routing table, and the routing table will specify to which IP we should route this traffic, and this connects to a component in our public subnet, another elastic network interface, and this interface is associated with our NAT instance. And this instance is just an EC2 machine. It's actually a spot instance, so it's very cheap. We're paying for a T4G Nano, so it's the smallest category. And we're going to see after we finish the design, we're going to have a pricing analysis here. This is extremely cheap. And this instance is it's running a AMI, like an Amazon managed image. And this image here, it is from an open source project called FCK NAT. And this project actually provides us with a very cheap way to connect our private subnet to, again, external resources. Now, you may be wondering, well, this feels very involved. Is there any way we could do that using, let's say, Amazon services? Well, yes, Amazon has NAT gateways and NAT instances as well that we could just get directly from Amazon, and we don't need to manage those. So we wouldn't need to manage an EC2 instance. Now, those can be very, very expensive, especially NAT gateways, because you're paying pretty much like per availability zone and per subnet as well. So, well, because they are fairly expensive, and again, going back to the scope of this project, we want to make something that, again, it's scalable, but also sustainable. I decided to go for a very simple, like very tiny EC2 instance running, again, this NAT being like a network address translation server. And that's pretty much how it works. This EC2 instance has a bit of like long-term storage associated with it, like EBS, elastic block storage, but again, very cheap. Now that we understand a lot of this networking, let's jump in and talk about our database and how our API service communicates with our database, right? Now, we know our platform API container is associated to an ECS task, and this ECS task has an IAM role here. This IAM role task role here actually has permission to connect to RDS Proxy. Because those permissions are within this role, that means the container, our Java application, can directly connect to RDS Proxy without providing a username and password. That's awesome because we, again, dealing with password rotations and general security, it tends to be a headache, and that definitely helps us with that. So Now, what is RDS proxy, right? So what is RDS actually? So RDS stands for Relational Database Service, and is yet again one of those services from Amazon. This one, more specifically, it helps us creating a database server. Now, if you're going to create a database server like from ground zero, what would you need to do? You would need to probably get a virtual private server, or again, a machine, and you would need to install your database engine within it. So you would have to install like MySQL or Postgres or whatever like database engine, and you would need to maintain that machine. Now, RDS comes to the rescue as a self-managed option where Amazon is the one responsible for setting up the server, installing the database engine, and make sure everything is updated and secure. And not only that, they have some options in terms of how you scale your database. So how many read replicas versus write replicas you're going to maintain, how much VPU and how much CPU and memory, and also, for example, what is your schedule for backing up your database. So there's a lot of interesting things that RDS provides us. Now, what is RDS Proxy? Well, RDS Proxy is a service that will help us manage connections to RDS. So again, imagine we have our Postgres database here, which we do. And again, our platform API is saving a lot of data. So like the user data, workflows, workspaces, everything is being saved in this transactional database in SQL, in this relational database, sorry. So the question is, how can we connect to this database, right? Obviously, the platform API, our Java application could connect directly to this database, which means for the database itself, you will need to create a socket connection. You will need to open a thread in its process, and this thread will consume obviously memory and CPU, and this thread will exist as long as this connection between our container and the database exists. And that's great. So why do we need this proxy? Well, this proxy is a way to manage and recycle connections whenever we have way too many of them. Because imagine, let's say I have 1,000 containers running my API now. Let's say I had to scale so many containers to receive and respond to thousands of requests that I'm getting to my API. Well, that's great. I'm going to have all those containers receiving traffic, but all those containers will then be creating connections with our database. And our database is going to be creating a thread within its machine. And again, a thread consumes CPU and memory, like stack and heap. So because of that, eventually the database will run out of resources. It's not going to be able to hold all of those connections, right? So RDS proxy is pretty much a broker. It is what we call maybe a PG bouncer, right? It's someone over here that we can ask our service to communicate with it first. And this guy will be the one responsible for holding the connections to the database and also recycling those. So for example, if I have 5 containers running my application code, maybe one container needs to do a query right now. It goes to the RDS proxy. RDS proxy has 5 connections. It lends one of those connections to the container. The container runs the query, it returns, and then RDS proxy brings back, like keeps that connection now, like it recycles it for maybe a next call that may come from another container, right? So RDS proxy is a nice way for us to make sure we're not going to be exhausting our database asking for way too many connections, right? We don't want to exhaust our database resources. Now, this over here in this design, it's an interesting decision, right? Especially given, again, we're trying to be cost efficient. RDS proxy is not a cheap product, but at the same time, I decided to include it in the design. That way, scalability doesn't go away as soon as we get to the database level, right? I wanted to make sure that if I decide, for instance, like have multiple copies of this service, I don't want to exhaust my database. And I have a very tiny database instance as well. And maybe in the future as well, I may have other workloads, let's say Lambdas or whatever it is, that may lead to, may require connecting to this database. And especially with Lambdas, I don't want Lambdas like creating connections and holding those connections straight to a database. Probably using, again, RDS proxy and having this recycle process happening would be nice, right? So again, it's an interesting component. I wouldn't say it's a hard requirement right now, but for the long run, to make sure we're not going to have I/O as a blocker for our application, having the proxy here helps a lot. And now that we cover RDS proxy, again, our PG bouncer, we can talk about RDS itself, right? So RDS is just, again, our Postgres database. We have a cluster with a single instance here. But again, we can, in this instance is serving as a write and read instance. But as we grow our application, we may add more read replicas to read, for example, workspaces, user data, and whatsoever. But so far, we're starting with a very lean database instance. And I believe this covers most of our design, right? All right, let's do a quick recap. We know our user makes API calls. Those are going to our CloudFront distribution, quote unquote, our CDN service. If the API request was already cached, the CDN service just returns the cache results. Otherwise, it redirects the request to our application load balancer here. And the load balancer keeps health checks on our ECS cluster, more specifically the platform API task, ECS task. Again, within this ECS task, we have all those containers, and our platform API container has a private IP. This private IP is associated with the ALB, and the ALB is always calling this container, doing health checks, making sure the service is up and running. And given the service is healthy, it then sends that request to the container, and the container may request like to do a few SQL queries to fulfill the request. So that the container then communicates with RDS proxy, gets a database connection, and with that database connection, then we're able to query some data from the database, or maybe insert data, update data, and that information go all the way back from the database to the container, to the load balancer, and then finally it goes all the way back to the user. And that's it. Now we know at least like how API calls are being resolved, and we also understand like how we're loading the actual web interface of our platform. Now, the last thing I want to cover, at least on this side of our system, which is our platform itself, right, is observability. We briefly talked about sidecars over here, and those sidecars from NewRelic, they are capable of fetching metrics. We talked about Sentry as well, receiving some exception data from the application code. But what about other components, right? What about our application load balancer? What about our CloudFront distribution? What about Cognito? What about like all those other cloud components? How can I observe if they are functioning correctly? And maybe, for example, I want to have a complete view of the requests being dispatched from my user browser to the CDN, then the ALB, then my compute, my servers, and then finally my database. How can I have this full view? Well, in order to have that, we are using NewRelic as a observability provider. So NewRelic is, again, an external service, and they offer two ways that we can observe our AWS account itself, like the AWS account components, right? Like the ALB, CloudFront distribution, etc. For that, there is a pull and a push way. For the pull way, it's pretty simple. We just create an IAM role in our account, and this it's called a cross-account role because we're giving access to NewRelic, more specifically NewRelic's AWS account, to access information in our account and pull that information, right? So AWS obviously offers a lot of APIs, and with those APIs and this role, NewRelic has its own workers, and those workers assume this role, and they're able to make those API calls to pull data from our AWS account. And with that data, we can understand what's happening with our ALB and all other components, right? Now, pulling is pretty good and it's pretty reliable, but also fairly slow, right? Getting real-time data from pulling, it's extremely hard because generally pulling happens every 10 minutes. I think from 5 to 10 minutes. You can think of pulling as like a cron job, like that is running every 5 to 10 minutes. That's great, but what if we want more like real-time data? Well, for that, there's a push method that we are also doing. So we're doing the pooling here. We're provisioning a role and giving that role to NewRelic. And again, everything is being done in infrastructure as code, including the NewRelic part. But we are also doing a push method here where there's a service called Amazon CloudWatch metric streams. And metric streams, you can imagine, aggregates all the information about our AWS account, and it can dispatch that information to a destination. In our case here, that destination is an Amazon Kinesis Firehose delivery stream. If you ever use Kafka or Pulsar or whatever like deliveries data stream service, Kinesis is fairly simple. It's just a data stream. So CloudWatch Metrics is pushing all of this data to this data stream, and this data stream is funneling this data to NewRelic. More specifically, a NewRelic endpoint that is ingesting this data in real time. Now, if Kinesis fails to deliver that information to NewRelic, like let's say, for example, we're sending a bunch of data, we're getting 200s back, but at some point we start getting 400s, 500s as an HTTP status, then Kinesis then sends and dispatches those failed messages to an S3 bucket to retry those messages later. So again, the push integration, it's very useful because it's going to give us more real-time information about our account. But the best way to approach this is having both pooling and pushing. That way, NewRelic has both of those pieces of information, and it obviously does deduplication and a bunch of other things on their side. But now we make sure we have the most up-to-date information about our AWS account components. In that way, we have a complete view of what's happening, once again, with all the traffic that is getting from the user to our architecture. And with that, I think we conclude, again, most of the components here in our system. The final part to talk about, which I'm going to talk very briefly, is CI/CD, right? So how are we releasing new versions of the web app? How are we releasing new versions of the backend? Well, for that, we are using GitHub Actions. So GitHub Actions, quite honestly, if you have used Circle CI or GitLab Actions or whatever CI service, they are pretty similar. We have, because our code is mostly hosted in GitHub, we have GitHub Actions associated, GitHub workflows associated with every single repository, and given specific actions like PRs or pushes to specific branches, we build our code and we push our code to our cloud, right? So in the case of the backend, for example, the platform API, whenever we have a new push done to the main branch, it automatically, we give GitHub an IAM role, more specifically using OpenID Connect, OIDC, and this role here running in our GitHub workers is capable of pushing a Docker image to our ECR repository here. So that's pretty useful, right? So you can imagine, like, whenever I push a new version of the API, maybe, again, I was developing things locally using my Docker Compose. I wrote some unit tests. I feel confident about my change. I make a PR. I merge that PR to main. As soon as I merge it to main, it kicks off a workflow process. This process builds my Docker image, and as soon as it builds it, it also pushes it to ECR. And whenever it pushes it to ECR, it also triggers ECS to release a new task definition, a new version of my service. And it makes sure that the new task is we have a blue-green deployment. It makes sure that the new task is healthy and it's going to start receiving requests, right? So this is pretty much like just a very quick overview on the CI/CD side of things. Also on the API side, whenever changes are made, we automatically create ERD, entity relation diagrams of the system, and those are automatically attached to the repository. I can actually show that really quickly here. So if we come here to platform API, we're going to see that we have a README here with this entity relationship diagram. This is not manually done. This is automatically done as part of our CI/CD pipeline. We also have API docs. So for our platform API, whenever we push new versions, we automatically create a swag YAML file, and that file then turns to be consumed by our Swagger UI, which is also hosted here in GitHub. So if we look for API docs, we can click over here in our pages, and there we go. We have live documentation of our API, everything working properly. Also, again, we have CI/CD workflows in our API here that for verifying our testing here and our test coverage. So anyways, there's a lot of good stuff that we're doing with GitHub Actions. Also with infrastructure and, again, platform front ends, we also have CI/CD done on infrastructure. So whenever we push Terraform code or Terragrunt code, automatically our CI/CD pipeline runs a bunch of pre-commits to make sure the code is secure, that we're not doing anything inappropriate, and it also runs a Terraform apply, more specifically a Terragrunt apply, and applies changes to our AWS account. And for the platform front end, same thing here. Automatically, whenever we push a new version of the front end, we actually build that front end. The front end is being doing with Vite or Vite, as you wish. And the framework produces HTML, CSS, and JavaScript, and we push those automatically to our CloudFront distribution over here. And we invalidate the cache in our distribution. That way, users can get the new version of the web app. Another thing that is being done is whenever we're pushing our web application also has observability, meaning that we are connecting it with Sentry and NewRelic. But in the case here, we're using the real user monitoring, the RUM integration of NewRelic with our web app. And we're also using Sentry here. So if we have exceptions that are running on the client side, we're able to capture those and observe those. And during the build process, we actually do something quite interesting. We make sure to build the source maps of our application, and we don't distribute the source maps together with the application itself. We are not serving the source maps, but we do dispatch the source maps to NewRelic and Sentry privately. That way, if an exception happens in our web application, because the source maps are available in those services, we're able to reconstruct the original code, and we're not like looking at minified code, right? So very helpful, very useful there. And I believe that covers most of, again, the system design for the Sigtunnel platform. The other side here I'm going to cover next is the workspace, right? Because we create workspaces in customer accounts. But I'm going to stop here for a second, and I'll come back and cover this other side. All right, so to quickly wrap up this demo, let's just talk about Sigtunnel Workspaces. So over here, I have a separate AWS account. So this is not where the platform is working. This is a totally different account. And this is what we call the customer account, right? It's whoever wants to integrate with Sigtunnel. Going back to the demo, we have workspaces, and whenever you create a workspace, you need to follow a few instructions. Those instructions here, it's pretty much how you run a Terragrunt module, a Terraform module, and this Terraform module will provision all of those components in your AWS account. So what are those components? Well, those components are a simple virtual private cloud, a simple VPC. Inside of it, we have a single public subnet, and we have an internet gateway, some routing tables, an Elastic network interface. And finally, within this VPC, we have an Elastic Container Service cluster, very similar to what we have here on the other side. Well, the difference here is this container, this cluster is empty. It's not running anything. It's not running any ECS service, as we can see here. Now, it's also using Fargate, meaning that we're going to ask Amazon to provision the machines, but this cluster here is empty. And whenever the user creates the workspace, so again, whenever they click create a workspace, they're going to have something like this. And within the workspace, we saw in the demo that we can create a set of workflows. And workflows, which are very simple here, they are translated to AWS step functions. And the step functions then, whenever we create a step function, we can call a set of resources. And being very oversimplistic here, our step function is capable of creating an ECS task on the fly with your code, with your worker code. And that worker code is, again, in Elastic Container, in an Elastic Container registry. And again, this is deployed in the customer's AWS account, so we don't have access to those Docker images. The customer creates the worker, it runs a GitHub action, and this action then, using OIDC, pushes the Docker image to this ECR. And again, this ECR gets consumed by the step function. So whenever we come here for example, a workflow, and let's say we edit, we're able to click in one of those, and we can see a list of Docker images. This list of Docker images are coming from the customer AWS account. It's coming from this Elastic Container Registry. Now, you may be wondering, okay, The customer ran this Terraform module in their account. How is it possible for us in our platform here to have access to their resources? Well, that's all being done because the Terraform module deploys an IAM cross-account role, right? This is the role that, going back to the workspaces, this is the role that we supply while creating a workspace. So this role gives us power in our platform API container here in our Java code to trigger the creation of step functions and also to trigger the creation of Amazon Event Bridge schedules. So if you recall in the demo, you can create a workflow, and you can also establish that you can also associate a cron expression to the workflow. And again, that cron expression, it is all done using Amazon Event Bridge Scheduler, and that is all executed in the customer account. So the customer has control over the servers, they have control over their Docker images, and all of the data, all the secrets that we inject into the step function, it is encrypted using a KMS key, like a key management service key from Amazon, an encryption key that pretty much encrypts all that data, and we don't have access to decrypt that data using the cross-account role. We can only encrypt data with this key. But anyways, I don't want to go into too much details. As an overview here, we have our API has a cross-account role, has access to this to the customer account via this cross-account role that we set up over here. And from that point on, we create all those necessary like step functions and event bridge schedules and a bunch of other things with this role here. And that's it. And from that point on, we can actually run a bunch of workflows, and we don't have to deal with all of this AWS like cloud management part, right? It's very simple. And I believe that concludes our system design overview. We covered everything under the sun here, and I hope you liked it. And if you have any questions, yeah, you can reach out on GitHub, LinkedIn, and I'll be happy to answer. See you guys later.